Foucault's pendulum. This pendulum, Foucault's pendulum. Foucault's pendulum. Foucault's pendulum. Foucault's pendulum. It is a simple device for conveniently detecting even slow rotation of the Earth and provide a direct experimental evidence that the Earth rotates about its axis from west to east once in 24 hours. It is a simple device. It is a simple device. It is a simple device for conveniently detecting even slow rotation of the Earth. Slow rotation of the Earth and provides a direct experimental evidence that the Earth rotates about its axis from west to east, once in 24 hours. Foucault's pendulum. It is a simple device for conveniently detecting even slow rotation of the Earth and provides a direct experimental evidence that the Earth rotates about its axis from west to east once in 24 hours. Construction. It consists of a very heavy mass. It consists of a very heavy mass. It consists of a very heavy mass. It consists of very heavy mass about 24 kg 28 kg in the original experiment, 28 kg in the original experiment performed by Foucault in Paris in 1851. Performed by Foucault in Paris. Performed by Foucault in Paris in 1851. Suspended by a very long wire. It is suspended by very long wire It is suspended by very long wire, 70 meters. Which meter? How many meters? 70 meters. 70 meters. 70 meters. Sorry, 70 meters. By a very long wire, 70 meters, so that the time period of the pendulum, time period of the pendulum, was large about 17 seconds. Was large about 17 seconds. 17 seconds. The attachment of the upper end of the wire allows the pendulum to swing with equal freedom in any direction. So that is period of oscillation in any plane is exactly the same. Such a pendulum, once set oscillation, continue to oscillate for a fairly long time. And next is working. When the pendulum is started its swing, the plane of oscillation is observed to process around the vertical axis during a period of several hours. If the pendulum were to be set up at the North Pole, of the Earth, it may oscillate as a simple pendulum. In a vertical plane, which remains fixed in an inertial or Galilean frame of reference, since the Earth under it rotates from west to east with an angular velocity omega. The plane of oscillation of the pendulum will appear to an observer on the surface of the Earth to be turning with angular velocity omega in the opposite direction, from east to west, to that of the Earth. It is not necessary that the pendulum should be situated right at the North or the South Pole. An apparent rotation of the Earth will be observed in any latitude except at the equator. Normally, the pendulum describes an ellipse, and by making it vibrate carefully, the ellipse can be made to approximate to a straight line, so that the pendulum swing in a vertical plane very approximately, that the motion of the bob of the pendulum will be along an ellipse. Under the various forces acting on it can be proved as under proof. Foucault's pendulum with its suspension along the vertical z-axis. The bob of the pendulum vibrates with a small amplitude in the horizontal xy plane. The bob of pendulum vibrates with a small amplitude in the horizontal xy plane When the bulb is displaced through a small angle, when the bulb is displaced through a small angle from its means position P to P dash, from P to P dash, when the bulb is displaced through a small angle, from its mean position P to P dash, the various external forces acting on the bulb are mg, acting downwards. The tension T in the string acting along P dash A, string along P dash A, and the Fixious force acting on it due to the rotation of the earth. If the net acceleration of the bulb is double differentiate of R double dash, if the net acceleration of the bulb is double derivative of R, then m double derivative of R equal to mg vector plus t vector minus 2m omega vector cross vector Va minus m omega cross vector R minus m d omega by dt cross vector R. Va vector equal to differentiate of R equal to the time rate of change of position. The time rate of change of the position vector. The position vector R of the bulb P, omega vector R angular velocity of rotation, velocity of rotation of the earth, taken as a rotating frame of reference, as a rotating frame of reference, minus 2 m omega vector cross Va vector equal to minus 2 m omega vector cross vector differentiate of R equal to Coriolis force. Minus m omega vector cross vector R equal to centrifugal force due to earth rotation. Centrifugal force due to earth rotation. The last factor minus md omega vector upon dt cross vector R equal to 0, as d omega vector upon dt equal to 0, omega vector being a constant, being a constant, a constant. In our treatment, we shall neglect the centrifugal force because its magnitude equal to mr omega square, and omega being a small quantity, omega square can be neglected. Omega can be neglected. 1 minute. In our treatment, we shall neglect it. In our treatment, we shall neglect the centrifugal force. Centrifugal force stands to 0 because its magnitude equal to mr omega square, and omega being a small then quantity omega square can be neglected approximately 0. The general equation of motion for a Foucault's pendulum is m double derivative of r equal to mg vector plus t vector, t means tension vector, minus 2m omega vector cross double derivative of r, single derivative of r. The composition of mr, the composition of m double derivative of r are m double derivative of x, m double derivative of y, and m double derivative of z. mg vector has only one component, in the vertical z. Detecting equal to mg and the components of t vector equal to tx, ty, and tz. As it is supposed that the amplitude of the pendulum is small and it vibrates almost in the xy plane, the components of r, the derivative of r along the z axis, z equal to 0, the Coriolis force is thereby given by the components of r. Sorry, 1 minute. As it is supposed that the pendulum is small and it vibrates. As it is small, suppose that the pendulum is small and it vibrates almost in, and it vibrates almost in the xy, almost in the xy plane, the components of the components of derivative of r along the z-axis is that z derivative of z equal to 0. The Coriolis force is therefore given by F Coriolis vector equal to minus 2m minus derivative of y omega sin lambda I plus derivative of x omega sin lambda j minus derivative of x omega cos lambda k. For the proof, the components of Coriolis force are along x-axis. The components of Coriolis force are along x-axis. The components of Coriolis force are along x-axis equal to 2m omega sin lambda differentiate of y comma along y-axis equal to minus 2m omega sin lambda differentiate of x along z-axis equal to plus 2m omega cos lambda differentiate of x. Hence the equation of motion in component from m double derivative of x equal to px plus 2m omega sin lambda y. Equation number 1, double derivative of m double derivative of y equal to ty minus 2m omega sin lambda differentiate of x and m double derivative of z equal to tz minus mg plus 2m omega cos lambda differentiate of x. Let x, y, z be the coordinate of the point P dash. Let x, y, z be the coordinate of the point P. Coordinate of the point P. X, y, z. X, y, z, the coordinates of the point P dash and the L length of the Foucault's pendulum. L length of the Foucault's pendulum. Then there are tx upon t equal to minus x by L r. Tx equal to minus tx by L and ty upon t equal to minus y by L r. Ty equal to minus ty by L and tz upon t equal to L minus z upon L r. Tz equal to t L minus z upon L. As the amplitude of the pendulum is small, z equal to 0. As the amplitude of the pendulum is small, is small, z equal to 0. So z equal to 0 and tz equal to t. Again as z equal to 0, then differentiate of z equal to 0 and double derivative of z equal to 0. Substituting tz equal to t and double derivative of z equal to 0 in equation number 3 we have. In equation number 3, this is equation number 2 and this is equation number 3. In equation number 3 we have 0 equal to t minus mg plus 2m omega cos lambda differentiate of x. The quantity 2m omega cos lambda x bar. The quantity 2m omega cos lambda differentiate of x is vertical component of Coriolis force. Is vertical components of Coriolis force. It is very small quantity and can be neglected. It is very small quantity and neglected. To compare to mg, then show t equal to mg. In equation 1 and 2 we get equal to mg. T equal to mg in equation first and second we have double derivative of x minus mg x by l plus 2m omega sin lambda differentiate of y m double derivative of y minus mg y by l minus 2m omega sin lambda differentiate of x. The time period of the pendulum is the time period of a pendulum is given by c equal to 2 pi under root L by G R 2 pi upon T equal to under root G by L. Let 2 pi upon T equal to omega 0, then G by L equal to omega 0 square. square. This is the equation number 4 and this is the equation number 5. Omega 0 square. Substituting G by L equal to omega 0 square in equation number 4 and equation number 5 we get double derivative of x equal to minus omega 0 square x plus 2 omega sine lambda differentiate of y and double differentiate of y equal to minus omega 0 square y minus 2 omega sine lambda differentiate of x. This is the equation number 6 and this is the equation number 7. And multiplying 7 by I, multiplying equation number 7 by I means under root minus 1 and adding to 6 we get double differentiate of x plus I double derivative of y equal to minus omega 0 square and in bracket x plus iy minus 2i omega sine lambda differentiate of x plus I differentiate of y r double differentiate of x plus I double differentiate of y plus 2i omega sine lambda differentiate of x plus I differentiate of y plus omega 0 square x plus I y equal to 0. Then x plus iy equal to u. Then derivative of u equal to derivative of x plus iy derivative and double derivative of u equal to double derivative of x plus I double derivative of y. Hence double derivative of u plus 2i omega sine lambda derivative of u plus omega 0 square u equal to 0. Substituting omega sine lambda equal to omega z. We get double derivative of u plus 2i omega z derivative of u plus omega 0 square u equal to 0. This is the equation number 8. The above equation in the operator form is put as d square plus 2i omega z d plus omega 0 square u equal to 0. This equation in the operator form is put capital D equal to d by dt and e square equal to d square upon dt square r d square plus 2i omega z d plus omega 0 square equal to 0. The two roots of the above equation, the two roots of the above equation are capital D equal to minus 2I omega z plus minus under root of 4 minus 1 omega z square minus 4 omega 0 square upon 2 equal to minus I omega z plus minus I omega 1 where omega 1 square equal to omega z square plus omega 0 square are capital D1 equal to minus I omega z minus omega 1 and D2 equal to minus I omega z minus omega 1. The general solution of equation 8 is 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 u equal to a e to the power minus I omega z minus omega 1 t plus b e to the power minus I omega z plus omega t omega 1 into t equal to a e to the power plus I omega 1 t plus I omega 1 t plus b e to the power minus I omega z t omega 1 t into e to the power minus I omega z t. This is the equation number 9. Where a and b are arbitrary constant. Where a and b are arbitrary constant are arbitrary constant we have stated above that omega 1 square equal to omega 0 square plus omega z square, where omega 0 equal to 2 pi upon t root L by g, angular velocity of oscillation of the pendulum, angular velocity of oscillation of the pendulum, and omega z, the z component omega sin lambda of the angular velocity of rotation of the earth, which is very small is compared to omega 0. Omega sin lambda of the angular velocity of rotation. Angular velocity of rotation of the earth and the earth is very small, small as compared to omega 0, as compared to omega 0. Omega z square can be neglected as compared to omega 0 square. Hence omega 1 square equal to omega 0 square plus omega z square equal to omega 0 square. Approximate or omega 1 equal to omega 0. Substituting omega 1 equal to omega 0 in equation 9. We get u equal to a e to the power plus I omega 0 t plus b e minus I omega 0 t into e minus I omega z t. This is the equation number 10. Considering omega z equal to 0, we get u equal to a e to the power plus I omega 0 t plus b e to the power minus I omega 0 t. The above equation gives the trajectory of the path traced out by the bob. The above equation gives the trajectory of the path traced out by the bob. Traced out by the bob. Now a e to the power plus I omega 0 t equal to a cos omega 0 t plus I a sin omega 0 t and b e to the power minus I omega 0 t equal to b cos omega 0 t minus I b sin omega 0 t. So a e to the power plus I omega 0 t plus b e to the power minus I omega 0 t equal to a plus b cos omega 0 t plus I a minus b sin omega 0 t. But u equal to x plus I y. So a plus b cos omega 0 t equal to x and a minus b sin omega 0 t equal to y. Squaring and adding we get squaring, and adding, we get x square upon a plus b, whole square plus y square upon a minus b whole square equal to cos square omega 0 t omega naught t plus sin square omega naught t equal to 1 which is the equation of an ellipse, which is the equation of an ellipse, with its center at the origin, with a center at the origin. Thus we find the trajectory. Find the trajectory of the bob of a Foucault's pendulum is elliptical. Of a Foucault's pendulum is elliptical. Assumptions. The following assumptions have been made in the treatment of Foucault's pendulum to show that the trajectory of the bob of pendulum is elliptical. First number, the amplitude of the pendulum is small. The amplitude of the pendulum is small. Second number, as omega the angular velocity of earth, as omega the angular velocity of the earth's rotation is small. Earth's rotation is small. The effect of centrifugal force. Centrifugal force mr omega square being proportional to omega square is neglected. Being proportional to omega square is neglected. And third number is the pendulum oscillates very approximately in the xy plane. The pendulum oscillates very approximately in the xy plane, and hence the components of vector r along along z-axis is that differentiate of z vector equal to 0. And fourth number, the vertical component of Coriolis force, the vertical components of Coriolis force 2m omega cos lambda differentiate of x is a very small quantity and is neglected as compared to mg. Neglected as compared to mg. Okay, thanking you. And next we will be solved about the example of this chapter. Okay, thanking you.